Good morning dear students. In the last video we learnt electric flux and also we had a derivation to find electric field at a point on the axial line of electric dipole. So in this class let us understand electric field at a point on the equatorial line of the electric dipole. So let us start the derivation. Look at the heading, electric field at a point on the equatorial line of the dipole. This question was asked in the year March 2015 and June 2019. Okay, so in order to understand this derivation, first we need to understand what exactly the dipole. Again, we will recall what exactly the dipole. Dipole is nothing but a pair of equal and opposite charges separated by a small distance 2a. Look at the diagram. Positive charge, negative charge. A pair of equal and opposite charges separated by a small distance 2a. So we consider dipole. And this is the midpoint of the dipole. And one more thing we have to understand to derive this equation, that is equatorial line. Even about the equatorial line also we discussed in the previous video itself. So equatorial line is nothing but the line perpendicular to the axis of the dipole. Look at this. This line is axis of dipole. Axis of dipole is nothing but the line joining negative charge and positive charge. To this axis we are taking one perpendicular line which is passing through the midpoint of the dipole. This perpendicular line is nothing but equatorial line. So our intention is we need to find electric field at a point on the equatorial line in this point. So in this point we need to find electric field due to dipole. And the distance between the point on the equatorial line and the midpoint of the dipole is taken as small letter r. And the electric field at a point P due to positive charge is directed outwards and it is represented by E plus Q, because this represents electric field due to positive charge. Look at the direction. The direction of electric field due to positive charge is directed outwards. We learnt in the previous class itself. Look at, it is directed outwards. Look at this. This is electric field at a point P due to negative charge E minus Q. Look at the direction. It is directed inwards. So these two concepts, when does it become outwards and inwards, we learnt in the last class itself. This is the angle. This is the angle. These two are the alternate angle to these two angles. Okay. Now let us start deriving the derivation. Electric field at a point P due to positive charge is represented by E plus Q. I'll write in terms of magnitude. Magnitude of electric field at a point P due to positive charge is represented by E plus Q. So according to Coulomb's law, 1 over 4 pi epsilon naught Q divided by the distance between the positive charge and the P is nothing but BP. According to Coulomb's law, BP whole square. But we need to calculate what exactly the BP, side BP. So we can calculate the BP by using Pythagoras theorem. So according to Pythagoras theorem, BP square is equal to, look at this, BP square is equal to R square plus A square, or A square plus R square. So I'll write R square plus A square. So in the place of BP whole square, I'll write R square plus A square. So equation become E, so here I consider plus Q, right? Plus Q is equal to 1 over 4 pi epsilon naught Q divided by BP whole square is nothing but R square plus A square, equation number 1. See, this direction of electric field due to the positive charge is along BP, along BP. Along the line BP. Similarly, electric field at a point P due to negative charge is represented by E minus Q. The magnitude of electric field at a point P due to negative charge, E minus Q. Since we are talking about minus charge, I'll write minus. Then same equation according to Coulomb's law, 1 over 4 pi epsilon naught. Q minus already have written here itself. Then what is the distance between minus Q and the P? AP. According to Coulomb's law, AP square. Now we need to calculate what exactly the AP square. Again we are using Pythagoras theorem. Similarly, AP square is equal to, look at the AP square. AP square is again R square plus A square. So R square plus A square. So I am going to substitute to this AP square. So E minus Q is equal to minus of 1 over 4 pi epsilon naught Q divided by AP square is nothing but R square plus A square. Equation number 2. Look at the direction of electric field due to negative charge is along PA. Along PA. So we got two equations. The equation 1 gives electric field at a point B due to positive charge. Equation 2 gives electric field at a point P due to negative charge. You just focus on the equation number 1, equation number 2. Both are equal in magnitude. That is, we can write E plus Q is equal to magnitude of E minus Q. Both are equal in magnitude. We need to find resultant electric field at a point P due to the dipole. To understand to find the resultant electric field, the vector E plus Q is resolved into two components along horizontal and vertical. Similarly, the vector E minus Q is resolved into two components, horizontal component and vertical component. Already you learned in the first PUC itself resolution of vector. Similarly, E plus Q vector or E vector plus Q is resolved into two components. Vertical component become E plus Q sin theta and horizontal component become E plus Q cos theta. Similarly, E minus Q vector is resolved into two components along vertical, E minus Q sin theta, along horizontal, E minus Q cos theta. I repeat, E plus Q is resolved into two components along vertical, E plus Q sin theta, along horizontal, E plus Q cos theta. E minus Q is resolved into two components along vertical, E minus Q sin theta, along horizontal, E minus Q cos theta. So here the component which are normal to the axis of dipole, normal is nothing but perpendicular. The components which are normal to the axis of the dipole, they cancel each other. Or else these two are equal in magnitude, opposite in direction, they cancel each other. The components which are along the axis of the dipole, means same direction along the axis of the dipole, add up. Means we need to add E plus Q cos theta, E minus Q cos theta to get resultant electric field at a point P. Resultant electric field, that is E plus Q cos theta plus E minus Q cos theta. So here I said E plus Q is equal to E minus Q, both are equal in magnitude, which means E plus Q is equal to E minus Q, we can write. So the equation become E is equal to E plus Q is nothing but E minus Q. We'll write E minus Q cos theta plus E minus Q cos theta. Look at this. In the place of E plus Q, I have written E minus Q only. Why? Because both are equal in magnitude. So E minus Q cos theta plus E minus Q cos theta become 2E minus Q cos theta. 2E minus Q cos theta. And we have a value for E minus Q. Where is E minus Q? Look at the equation number 2. Along with the minus sign, I am going to substitute here. First I will write the minus sign, minus 2. E minus Q is nothing but what? 1 over 4 pi epsilon naught Q divided by R square plus A square into what we have? Cos theta. Now I am going to simplify the equation like this. 1 minus 1 over 4 pi epsilon naught 2Q divided by R square plus A square cos theta. So we need to find cos theta. So value of cos theta can be understood by taking the triangle PAO or POA. So from the triangle PAO cos theta. Cos theta, what are the sides for the cos theta? Adjacent by hypotenuse. So triangle PAO. Look at the triangle PAO. To this angle, this is opposite, this is adjacent, and this is hypotenuse. Cos theta is adjacent by hypotenuse. What is the adjacent value we have? A. So adjacent value is A. And what is the hypotenuse value we have? AP. So I will write adjacent is A and divided by hypotenuse is AP. And also we know the value of AP whole square. In the beginning only we learnt. Right here, AP square is equal to R square plus A square. But we need a value of AP. So AP become root of R square plus A square. So we got the value of AP. Now I am substituting here. Therefore cos theta become A by root of R square plus A square. Now I am going to substitute this cos theta value to here. So it become E is equal to minus 1 over 4 pi epsilon naught 2Q divided by R square plus A square cos theta. What is the cos theta value we have? A divided by root of R square plus A square. E is equal to, look at this equation, minus 1 over 4 pi epsilon naught 2A divided by R square plus A square cos theta. What is the value for cos theta we have? A divided by root of R square plus A square. Here nothing is there means power 1. Here the what is the value of root? 1 by 2. So if you simplify this, you will get 4 pi epsilon naught 2QA can be written as Q into 2A. And if you simplify this denominator, you will get R square plus A square to the power of 3 by 2. Because here the power is 1, here the root value is 1 by 2. But Q into 2A, Q into 2A is nothing but what? P, that is electric dipole moment. So the equation become minus 1 over 4 pi epsilon naught. In the place of Q into 2A, I am writing P, then divided by R square plus A square power 3 by 2. Now, if the dipole is small or short, which means R is very much greater than A. If the dipole is short, that is R is very much greater than A, then A square can be neglected compared to R square. So we need to neglect A square since the dipole is very small. So neglect A square, and what will be the remaining equation we have? Minus 1 over 4 pi epsilon naught P divided by neglect A square. What is the remaining thing? R square to the power of 3 by 2. So 2 get cancelled. What is the remaining equation? I'll write the remaining equation here. E is equal to minus 1 over 4 pi epsilon naught P divided by 2 get cancelled. The remaining thing is R cube. So this is the magnitude of electric field at a point on the equatorial line of the dipole. Here one thing you can notice, here we have minus sign. The minus sign clearly indicates that the direction of electric field and the direction of electric dipole moment. We learned the direction of electric dipole moment is always from negative charge to the positive charge. Look at this, negative charge, positive charge. So the direction of electric dipole moment. Electric dipole moment is represented by P. So P vector. Look at the direction. The direction of electric field and the direction of electric dipole moment are in opposite direction. Electric field and electric dipole moment are in opposite direction. So negative sign clearly indicates that electric field and electric dipole moment are in opposite direction. We can express in terms of vector form. I'll write the vector form here. E vector is equal to minus 1 over 4 pi epsilon naught P divided by R cube P cap. Instead of using R cap, here I am using P cap. So P cap represents unit vector in the direction of electric field. So in this derivation we learned electric field at a point on the equatorial line of the dipole. Dipole, this is equatorial line. At a point on the equatorial line, we found the electric field, that is equal to E is equal to minus 1 over 4 pi epsilon naught P by R cube. Here the negative sign represents or indicate that electric field and electric dipole moment are in opposite direction. This derivation is important for 5 marks. Next concept is torque acting on a dipole placed in a uniform electric field. So before going to the concept, we must know what exactly the torque or what is uniform electric field. About a uniform electric field and non-uniform electric field we learnt in the previous class itself. Uniform electric field can be represented by equally spaced parallel straight lines. So these equally spaced parallel line represents uniform electric field. Inside the uniform electric field, I kept or we placed dipole. Dipole is nothing but what? Equal and opposite charges separated by a distance 2a. Look at the dipole, minus q plus q separated by distance 2a. And this the direction of or axis of the dipole makes an angle theta with the direction of electric field. So look at the consideration, minus q plus q or the magnitude of charges of the dipole, minus q plus q. 2a dipole length and theta angle between the dipole axis and the direction of electric field. This is the dipole axis and this is the direction of electric field. It makes angle theta. So our intention is we need to find torque which is acting on a dipole placed in uniform electric field. Torque is nothing but rotating force or twisting force, which means when the dipole is placed in a uniform electric field, it experiences a torque, which means it rotates. Let us understand along with the derivation. Now look at this, negative charge and positive charge dipole placed in uniform electric field. When a charge is placed in a uniform electric field, it experiences force. The magnitude of the force is given by F is equal to Q into E. How does it become F is equal to Q into E? Let us understand by using a small diagram. This is point charge Q placed at a point O. This point charge will produce an electric field, say E vector. So here electric field is nothing but force experienced per unit positive charge placed at that point. We have an equation for that. So electric field is nothing but F by Q. Q is a unit positive charge. So if you simplify for F, F is equal to Q into E. So the magnitude of the force experienced by a charge placed in a uniform electric field equal to F is equal to Q into E. That is what I written here. The force experienced by positive charge, F is equal to QE, it is along the direction of electric field. Look at the direction. But whereas the force experienced by negative charge is equal to F is equal to minus Q into E, opposite to the direction of electric field. Opposite to the direction of electric field. So what we get, the two forces, that F is equal to Q into E, F is equal to minus QE, both are equal in magnitude but opposite in direction. Since the total force acting on a dipole is 0. Why it is 0? Two forces, you just add two forces, plus QE minus QE. So what will happen? Cancel. So the net force acting on a dipole is 0 when the dipole is placed in uniform electric field. So this is force experienced by a positive charge, force experienced by negative charge. So the total force or net force acting on a dipole is 0. Since both the forces are equal in direction, these forces constitute couple or tends to rotate a dipole in clockwise direction like this. This force is along the direction of electric field. This force is along opposite to the direction of electric field. So dipole will rotate like this. Dipole will rotate like this. Then the magnitude of the magnitude of torque acting on a dipole can be calculated by using an equation, that is torque is equal to magnitude of either force into perpendicular distance between the forces. So this is the equation to calculate magnitude of torque acting on a dipole. Look at the equation, magnitude of either force into perpendicular distance between the force. Magnitude of either force means we have a two force, you can take any one. Torque is represented by tau. The symbol tau is equal to magnitude of either force. I will take Q into E into perpendicular distance between the force. Look at the perpendicular distance. This is F is equal to Q into E. This is F is equal to minus Q into E. Between we have a perpendicular distance. The perpendicular distance between the two forces is AC. So we need to calculate the value of AC. So for that I am considering the triangle BCA. From the triangle BCA, look at the triangle BCA. For this angle, simplify it for sin theta. Sin theta is opposite by hypotenuse. So to this angle, what is opposite we have? This is opposite, adjacent, hypotenuse. What is opposite we have? AC divided by, what is hypotenuse we have? Hypotenuse is nothing but AB. So we have to solve for AC because we are finding the value for AC. So AC is equal to AB sin theta. But AB is equal to what? Look at the diagram, you will get AB is equal to what? Dipole length, that is 2A. So in the place of AB, I can substitute 2A. So AC become 2A into sin theta. 2A into sin theta. Now I am going to substitute the value of AC to this equation. Then tau is equal to QE into AC is nothing but what? 2A sin theta. So I am going to simplify this equation as tau is equal to, I will write first Q 2A E sin theta. Same thing, I simplified the equation. QE into 2A sin theta can also be written as Q2A E sin theta. But here Q into 2A, we know that Q into 2A is nothing but what? Electric dipole moment, that is P. So tau is equal to, in the place of Q into 2A, we are writing P. So PE sin theta. So this is the magnitude of torque acting on a dipole. We can write in terms of vector form. In vector form, tau vector is equal to P vector cross E vector. And we have two cases. Let us check it out. When does the torque become maximum and minimum? Case 1. When theta is equal to 0 degree. By using this equation, then tau is equal to PE sin, in the place of theta, 0 degree. Sin 0, 0. So tau is equal to 0, that is minimum. Case 2. When theta is equal to 90 degree. By using this equation, tau is equal to PE sin 90 degree. Sin 90 is 1, the remaining thing, tau is equal to PE maximum. Look at this. When theta is equal to 0 degree. When theta is equal to 0 degree means the direction of electric dipole moment is along the direction of electric field, which means we kept like this. Instead of keeping like this, if we kept like this, means the direction of electric dipole moment and the electric field are in same direction, then theta is equal to 0 degree. When the dipole is placed along the direction of electric field, then the torque is 0. The torque acting on the dipole is 0. When the dipole is placed perpendicular to the direction of electric field, 90 degree, the torque acting on the dipole is maximum. One more case is there. When theta is equal to 180 degree. 180 degree is nothing but the dipole is placed like this. Means the direction of electric dipole moment is opposite to the direction of electric field. At that situation, the dipole is in unstable equilibrium. So in that case also the torque acting on the dipole is 0. Here the torque is a vector quantity. I will write here, note, torque is a vector quantity. And the SI unit of torque is, look at this equation, SI unit of electric dipole moment is coulomb meter into the SI unit of electric field is Newton per coulomb. So coulomb get cancelled. So SI unit of torque is Newton meter. SI unit of torque is Newton meter. Now the torque is a vector quantity and the SI unit of torque is Newton meter. Two important things we need to understand which regards torque acting on a dipole. Already I explained. See the first point, when dipole placed in a uniform electric field, it experiences only torque. The net force on the dipole is 0. That is what we studied. So dipole placed in uniform electric field, it experiences only torque. Torque also called as couple. But the net force acting on the dipole is 0. Why? Because these two forces are equal in magnitude and opposite in direction. Then the next point, see here, whereas it experiences torque and net force when placed in a non-uniform electric field. Same dipole, instead of keeping in uniform electric field, if it kept in non-uniform electric field, it experiences both torque and net force. Look at the second point. The direction of torque can be determined by using right hand screw or curl rule. So how can we understand the direction of torque? For example, you just consider this as a dipole. The dipole is rotating like this. The curled finger indicates the direction of dipole. If the dipole is rotating like this, then the direction of torque will be like this. The thumb indicates the direction of torque. The dipole is rotating like this, so the direction of torque will be in this direction. So according to this, look at this, the dipole is rotating like this. The dipole is rotating like this, so the direction of the torque is perpendicular to the plane of the board. Perpendicular to the plane of the board. Why? Because the dipole is rotating like this. Like this. The direction of torque is like this. So in this class, we derived two derivations. The first derivation gives the electric field at a point on the equatorial line of the electric dipole. The second derivation, from the second derivation we understood that the torque acting on a dipole placed in a uniform electric field. So in the next class we will discuss another few concepts. Thank you.